Okay, so this is chapter 3, part 2. I kind of overworked my voice on the last one, so we'll see. Well, that doesn't concern you. That's for me. But anyways, all right. So we're not going to cover the geometric distribution just because I'm finding there's not enough time, and that's okay. So, but we are going to cover the binomial distribution. So the only distribution that we've talked about so far is the normal distribution or a skewed distribution. Okay, so we've talked about a few. A skewed distribution, a bimodal distribution. And so a binomial distribution is a little bit different. So a binomial situation is when we only have two possible outcomes. So usually we boil it down to success, failure. Other options are kind of yes, no answers. Often we talk about pretty morbid stuff like, did a person die or did they survive? Right. And there's only really two options. So especially if you're studying diseases, that type of thing, then often what you're interested in is whether a person died from this disease. And so that uh, would be the thing that we're interested in. And unfortunately, just kind of we call that a success. So whatever we're interested in is a success. Okay. So whatever we are interested in, or whatever event, that's what I wanted to say, whatever event we are interested in is called the success, right? And then if that event didn't happen, then that's considered a failure, right? So died, survive is pretty common for binomial situations. Passed, failed, right? So as long as you have only two possible outcomes, right? And a lot of the time you could boil it down and force it to be two possible outcomes. For example, you can be in either first year, second year, third year, fourth year, or fifth year if you're taking a little victory lap. I did. There's no shame in that game. Right. So, but you can be in one of those. But what we could do is we could talk about: are you in first year? Yes or no. Right. And so if you are in first year, that's a success. If you're not, if you're in one of the other years, then we would call that a failure. Right. And so a lot of the time you can kind of force a binomial situation by just considering one of the outcomes as a success and the rest as failures. The key is that each outcome, besides having only two outcomes, each outcome has to have a fixed probability. What does that tell us? Well, we know from the probability section, right? Chapter 2. We thought we left that in the rear view mirror, sort of. This is the last time that it's really going to come back to haunt us for the binomial distribution. And then we'll kind of package it and put it away. But there's a nice tie-in with the normal distribution and the binomial distribution. So that's why it's coming in this place here. So each outcome has to have a fixed probability, which means what? It means that all the outcomes have to be independent of each other, right? Independence has to do with the probability. Knowing that one outcome happened doesn't affect the probability of the next outcome, right? It stays the same, and that's the definition of independent events. And so each outcome has to have a fixed probability. Really what we're saying is these probabilities have to be independent, or these events have to be independent. Now, introducing a few kind of a little bit of notation here. N is the number of trials. We're used to seeing lowercase n as the sample size. Fine. Now n is the number of trials. That's a pretty reasonable kind of connection to make, I think. So n is the number of trials. How many times did you try to get a success. N is the number of times you tried to get a success, right? And then we're going to see what, and we'll denote it by K, a lowercase k, successes. So N is how many times you tried to get a success, and K is the actual number of successes. Okay. If you think about flipping a coin, you flip a coin 10 times, that would be the number of trials. And then whether you're interested in heads or tails, it doesn't matter. Let's say you're interested in how many tails you got, then K would be the number of tails that you saw in those 10 flips. Good. So I want to do an example here to kind of illustrate where the formula that we're going to use for this section comes from. Now, I am not a sporty person. I've never really done sports. I was very much like a lone wolf, did swimming, horseback riding, yeah, never shooting hoops. No. So this isn't me, but I'm shooting hoops. So forgive me if the terminology is off. Anyways, and I know the probability of each shot going in is 0.2. Probably a little bit lower for me, to be honest, but that's okay. If I shoot 3 times, what's the probability of exactly 1 shot going in? Okay. And I'm going to define S only because I use S later as a success. And so first thing I want to do is, how about capital S is going to be, well, if I want to know what's the probability of exactly 1 shot going in, then, and I know, so from the probability that I'm given, right, it's the probability that a shot is going to go in. And so a success is it going in. I don't know if I'm saying that right, but I think we all understand. So the shot, so a success is a shot going in the hoop, in case that wasn't clear. I don't know, doesn't matter. So let's take a step back. Do we have a binomial situation here? I only have 2 outcomes, either it goes in or it doesn't, right? And I know the probability of each shot going in is 0.2. So the probability stays the same throughout. So is this a binomial? Oops. Binomial, yes, because we can break it up into success is going in, failure is not going in, right? And those are the only 2 options that can happen. And events are independent, or maybe I'll specify the event is the shots. So, and shots are independent. Okay. So first thing you want to do is just identify, is this a binomial situation or not? Now, for small versions of the binomial, you can definitely just use the tree diagram that we introduced in chapter 2, right? And so how I want to solve this problem is first using the tree diagram to show you that you already know how to solve this problem, but then using the binomial distribution, we can expand it to quite a few more trials, okay? So with only 2 outcomes, right, at each shot, And I think I'm only shooting, so if I shoot 3 times, okay, I'm going to draw this tree diagram just to have a look and see. I'll draw it probably a little bit nicer later, but here's the tree diagram. Oops. So shot number 1, it either goes in or it does not. I'll use the complement of a success instead of a failure, just to indicate that it either is a success or it isn't. So then I move on to shot number 2. And depending on what happened in shot number 1, I can still have a success or not in either of these branches. Okay. Now that you're kind of seeing the pattern, right, you can see how 3 shots, it gets to be quite a large tree, right, already. So the third one here, success, not a success, success, not a success, success, not a success. I have to squeeze them in here. Success, not a success. Okay, so this is only with 3 trials, right? And I'm using a generic success, not a success, just so you can see that it applies to any of these binomial situations, right? And so now imagine you're flipping a coin even 5 times, right? So here are the first 2 flips. Now you have to do 2 more layers, but each of these get 2 branches, and then each of those get 2 branches, and it just so quickly gets out of hand, right? So you can see, uh, you can see uh, that the tree diagram quickly gets out of hand. For more than 3 trials. Oops. Right? And so I'll even put an exclamation mark here. Okay, we're going to use it because we are only thinking about 3 trials. Here's the tree that we're going to use, right? And so we can solve it, and you can solve it this way, but once we start talking about 10 trials, oh my gosh, can you imagine? No, thank you. So just keep that in mind, right? So that's why we need this formula that we're about to develop. Yeah. Now let me pause and clean up these notes here. Okay, there wasn't much to clean up yet, but so what did it say here? Oh yeah, so we're gonna solve it 2 ways. First, I want to show you with the tree diagram just to show you that, yes, you know what's going on here. And then I also want to introduce the binomial distribution to calculate these probabilities. And you'll see that it's a little bit easier once you get the hang of it. Okay, so first let's start with the tree diagram. And you know what? I'm just going to copy this here. It's not pretty, but it definitely works. Paste. Can even make it a little bit bigger. Okay. So I think the question, what was the question? I'm forgetting. If I shoot 3 times, what's the probability of exactly 1 shot going in? Okay. Now, there are a couple of ways that that can happen, right? So what we want to find the probability of exactly one shot going in. Now, I will jot down here in the top ones that the probability of success was 0.20. And so the probability of a failure is 0.8. And that remains the same for all of these. And maybe I'll pause while I jot those down, but you can. Okay. So if we want exactly one shot going in, it doesn't specify where that success has to be, right? We just know that there has to be exactly one. So I'm going to start over here on the, okay, the first shot went in. What does that mean? Well, it means that if I have the first shot going in, the only other option that satisfies that criteria of exactly one shot going in is if the rest of the shots do not, right? And then at the end of that branch, that's one of the probabilities of exactly one shot going in. In fact, it's the probability that the first shot is the one that goes in. Okay. And then if we head over to, okay, so the first one didn't go in. So then let's think about if the second shot goes in, well, then the third shot can't go in if it has to be exactly one, right? Or if the first one doesn't go in and then the second one doesn't go in, then if the last one goes in, that satisfies the criteria. So what we can see is that we have 3 branches that satisfy the criteria of exactly one shot going in. And I think I actually have it typed up, so I'm not going to write it out. I did. Notice that what happens is that because the successes and the failures all have the same probability, or the probabilities stay the same throughout, so then the order doesn't actually matter, but we need to take the different orders into account. So it could be this first branch, or, and remember, to get the probability at the end of a branch, you multiply down, right? Because we're saying we have to have a success and a failure to end up at the bottom of this one. And so whenever you're saying and, remember, you're multiplying down the branches. But then when you're looking at the different branches, you're saying, okay, well, it could be this first branch, or the second branch, or the third branch, right? And so whenever you're saying or, you end up adding. So using a tree diagram, we can see that there are 3 ways of getting exactly one success, and that's what we saw. To find the probability of each branch, we multiply the probabilities down the path, right? And so here I've listed them, all the probabilities, and of course they're going to have the same probability because nothing's changing. You're multiplying A times B times C is the same as C times B times A, right? And so of course they're going to have the same probability, but we need to remember that there are 3 options. So the probability of exactly one success are all these probabilities, all these 3 probabilities added together, which puts us at 0.384. So the probability of exactly one success in 3 trials is 0.384. Okay, so that's good. So we know how to do that. It's a little bit tedious, but we know those mechanisms, and we have done that before. So now I want you to remember that you know how to do this when I introduce the binomial distribution. Now let me just bring in all this here. Oh, you know what? I gotta delete some pages. Oh, BRB. Okay, so to be able to deal with basically more than 3 trials, right? Even if we only have 2 possible outcomes, it gets completely out of control pretty quickly. So in order to be able to deal with any number of trials, we're going to use the binomial distribution to calculate the probability of k successes in n trials. So we need to introduce a couple of things here. We're going to let x be the random binomial process. And so x is just saying, hey, I follow a binomial distribution. Okay, great, cool. The probability of that x equals k. Remember, k is the number of successes, right? So I've got them here. I almost wrote them down again, but then I saw them here. So the probability that x equals k is, this is the choose function, n choose k. And if you haven't seen that before, I will show you how it works and what to do. But for now, you read it as n choose k. And it's down here. So n choose k is how we find the number of ways that we could get k successes in n trials. So when we set up that tree and we found that there were 3 ways that we could get exactly 1, right? What we're finding is the probability that x equals 1 is 3 choose 1, right? Because we're doing 3 trials and we want k successes. 3 choose 1, which turns out it's going to be 3, but we're going to confirm that. And then times p to the power of k. Now, p is the probability of success. Okay? So in our case, it was 0.2. And then times 1 minus p, which I'll often write as q. P is the probability of success, and q is going to be the probability of failure. But q is just 1 minus p. I'll even highlight that because that throws people for a loop sometimes when I write q, but it's just 1 minus p. So then you have the probability of a failure to the power of what? Essentially, however many failures you have, right? N is the number of trials. Subtracting the number of successes, well, that should leave you with the number of failures, right? And so you have the probability of a success to the power of however many successes, right? And we saw that pattern here, right? We had 1 success in each of these. So we had 1.2, and then we had 2 failures regardless of the order. So we had 0.8 to the power of 2, right? So we've seen the structure before, but now here it is as a formula. The only weird part is the choose function. So I want to spend a little bit of time, but before I do that, n minus k is the number of failures, right? In case you don't see that right away. Okay, so n choose k, how does it work? What does it do? I'm not going to use the formula that's behind it. I'm just going to use your calculator, because any scientific calculator that you can get your hands on will have a choose function. So where did it go here? Let me grab these here. Whee. So like I said, in this example, we wanted to find, we had n is the number of trials, right? So 3, and k is the number of successes that we're interested in for this one probability. And so it's 1 in this case. So we want to find 3 choose 1. So we already know we're expecting 3, right? But we can check it on our calculator. Usually it's called NCR. And usually you'll want to maybe Google your own calculator. Usually what you end up doing is you hit the number. Usually hit the first number 3, then the NCR button. For me on this one, I don't know if you can see, it looks like that. So it's a second function. I'm going to bring up the Desmos calculator. And it's in the functions. And so it has this NCR function. It's a little bit different because it wants NCR and then the numbers 3, 1. Okay. And it tells us that it's 3. Okay. So just to help you figure out how to use your calculator to find the choose function or to use the choose function, I want you to do a quick run through and make sure that when you do 10 choose 2, you get a result of 45. Okay, so in 10 trials, how many ways can you get exactly 2 successes? Can you imagine building that tree and having to trace, okay, so now I need exactly 2 successes, right? You're going to end up with 45 different paths, and it's a no for me, right? I'd rather use the choose function. So I'm going to show you on the Desmos calculator here, but I want the NCR of 10, 2 end bracket, and I get 45, so that's good. I've got a side note here that you really need to be able to recognize when your calculator is giving you scientific notation, because sometimes it's very, very subtle. Okay, so this one is an engineering calculator, so it does it. And you might not even be able to see, but I've also got this business math calculator. Great for doing like business math, terrible for everything else. But so for example, this 100 choose 45 is going to yield some scientific notation because it's a huge, huge number. 10 to the power of 28. So you have to move this decimal 28 bumps to the right. It's massive. So, but as a test, that's the one that you can use to make sure that you are able to recognize when you get scientific notation. And I'm not even 100% sure if this calculator, oh yeah, okay, so I wonder if I can show it to you. Do you see how it has the numbers and then it just has a subtle space here? And of course it's mirror image, so it's like weird for you to look at, but so it does have this little space, and that is supposed to tell you that it's times 10 to the 28. So that's why I want you to test it out, make sure that you're able to recognize scientific notation, and also just know how to use your choose function, right? And there are a couple of other examples. A couple of other examples here that you can use to just confirm that you're getting the right answer. So back to, actually, pause it here. Okay, I'm ready. It's only because I saw this today, and well, I thought it was pretty funny. And then I had, so it's all I could think about when I had this little typo here. Oh, well. Of all the typos, that one's not so bad. All right, so back to business. Where was I? Okay. So what we can do is we already confirmed that 3 choose 1 was 3. right? And I'll even do this. Because what we can do is we can now, oh, well, now it's gonna, oh well, diagram, all for the gram. Okay, so we can confirm our calculation from the tree diagram using the binomial distribution. So in general, right, the probability that x equals k, k is going to be the number of successes. And so is n choose k, p to the power of k, 1 minus p to the n minus k. Okay, so now there is a typo here. That should be 1. The probability that x equals 1. So this is only going to give us the probability that x equals 1, exactly 1. Okay. And so, but that's what we want in this case, but it's not necessarily what we want later on, right? What's the probability of at least 1, right? That kind of thing. So, but we're getting there. So the probability that x equals 1 is 3 choose 1, which we'll later replace with just 3, times 0.2. That's the probability of a success to the power of 1, because we only want 1 success. So that's 0.2. And then 0.8 to the power of 2, because we want 2 failures. 1 success, 2 failures. And ta-da! This is not very surprisingly the same result as we found using the tree diagram. Oh no, I just realized this is important. How come it won't? There. I had to click it, didn't I? Okay, well, you can probably fast forward while I sort this out here. Maybe. Okay. Hey, it even got sorted out. Okay. Now I'm happy. I can't touch it though. So this is the same result that we found. Now I'm back. Okay, sorry. That's why I pause it. I just got caught up. Okay. So that's the same result that we found. So, and that's not surprising. That was the whole goal of it, right? And so now hopefully you're feeling a little bit more comfortable with kind of tying in that tree diagram and saying, oh, I don't really want to do that anymore. I think I should just buckle down and learn the binomial distribution. It is on your formula sheet, of course, which I'll bring in at the once I've introduced the mean and the standard deviation. What? I thought we were talking about binomial distributions. We are. I know, weird, right? So, old habits. Cut it out there. Okay. So what's kind of neat is that we can still find the mean and the standard deviation of a binomial distribution. How can that be? So we have a number of trials, we have the probability of a success, and so if I flip a coin 10 times, how many tails am I expecting to see? 5, right? Why is that? Well, it's because the mean, which we have called the expected value before, and in this case, it makes a little bit more sense to call it the expected value. And it highlights that it's what we would expect to see, right? And so the mean is always what we would expect to see. If we don't know anything, at least that's what we would expect. Okay, so a binomial distribution with n trials and a probability p of success. You don't need to worry about this notation, but that's just how it is. That's how it's denoted. So it has a mean mu of n times p. So if we think about flipping a coin 10 times a probability of a tails is 0.5, 10 times 0.5, well, that's 5. So that's where that comes from. We also have a standard deviation, and the standard deviation sigma is the square root of n times p times q. And I've put it here, but I should probably, where q is 1 minus p, right? So here I'm using that shorthand notation. I'm going to show you on the formula sheet that you have all this on the formula sheet, right? So you don't need to memorize any of this stuff. It's all going to be there, but the problem is it can be hard to identify a binomial situation and to know to use the binomial distribution, and also the calculation, right? This is a lot of calculations. Okay, good. Let's see here. All right, looks like we've got an example. I'm going to clean this up. Okay, so what I want to do is go through an example, but like we did earlier, or I guess last day or whatever, it was earlier today for me. So anyways, let's go through and read through the problem, and then I encourage you to pause it and work through these problems on your own, and then you can kind of fill in the gaps and work through it with me after. Okay, so the S&P 500 index has a probability 0.56 of increasing in any week. Assume the change in the index in any given week is not influenced by whether it rose or fell in the previous week. That is a little bit of a stretch, right? But it says to assume it, so okay, great. Let X be the number of weeks among the next 5 weeks in which the index rises, right? So we want to know how many possible outcomes are there each week. Yeah. I will say this, you don't want to forget about 0 increases, right? So 5 weeks, we have 5 trials, right? And so we could have, well, 5 increases, right? So an increase in every week. You could have 4 increases, you could have 3 increases, you could have 2 increases, you could have 1 increase. And like I said, don't forget, you could have 0 increases, right? So that's also an option. Success in this case, there are 2 signs pointing towards it, right? So the probability that we're given is the probability of it increasing. So a success in that case would be increasing. But also we want to know X is the number of weeks among the next 5 weeks in which the index rises. So again, it's telling us that it's the index rising. Here to kind of shape you a little bit, if this said let X be the number of weeks among the next 5 weeks in which the index decreases, right, then, or falls, then the probability of a success would be 1 minus this, right? So it really hinges on what you're defining the success to be. And in this case, it's increasing, but you might have to play around with it because the probability of a success has to match what you're calling a success. What are N and P in this case? Leave that to you. What are the possible values of X? Okay. Leave that to you to try. What is the probability of the index increasing in more than 3, not including 3, just to clarify, of the weeks, meaning 4 or 5, right? And then what's the mean and the standard deviation of this distribution? Okay. So, like I said, pause it, try it, come back, and we'll work through it. I realized I muddled it. How many possible outcomes are there each week? I was thinking as I took the dog out, I'm like, well, that's so weird. Why would I ask for 0, 1, 2, 3, 4, 5 twice? I didn't. How many possible outcomes are there each week? I led you down the wrong path, didn't I? Well, it can either go up or down. So 2. So let's go through these. 2. Increase or decrease. We're actually going to assume that they maybe we'll lump staying the same into one of these categories. I'll put it with the decreasing. So increase or no increase. Clever. Right? Because then we don't have to worry about it staying the same or what have you. Identify what a success is in this case. We already talked about that, right? So a success is an increase. What are N and P in this case? N is the number of trials, right? And so that's the 5 weeks. And P is the probability of success, which was 0.56, because that's the probability of increasing. Okay. What are the possible values of X? Here it is. That's the one that I jumped the gun and went to right away. X equals, and you're allowed to do this. It's you can just list them as possible outcomes. So 0, 1, 2, 3, 4, 5. Right? But it can only be one of these, making them disjoint, right? So here, don't forget about 0. That's probably the biggest one that people miss of these. So now we want to find the probability of the index increasing in more than 3, not including 3 of the weeks. So we can write that out, just kind of translate it into words. It's the probability of an increase in 4 or 5 weeks, right? Which in terms of the probability notation and the binomial distribution, well, the binomial distribution can only give us the probability of exactly 4 or exactly 5, right? And so what we have to do if we care about 4 or 5, then we have to find those probabilities individually and add them up, right? Because for the probability of 4 or the probability of 5. So I'm going to scoot this over just a smidge here. And this becomes the probability that X equals 4 plus the probability that X equals 5. Okay. I would probably find these individually, right? I would find the probability that X equals 4 because it's a fair amount of work, and then the probability that X equals 5, and then add them up. So then come back to this. So let me just add a page here. So we can do that. And maybe give myself some room here. So the probability that x equals k in general, so I'm going to write out the general formula, is n choose k. And I don't want to see a line here. It's not a fraction, right? It's its own function that looks like this. P to the power of k times 1 minus p to the power of n minus k. Right? So then the probability that x equals 4, which is going to take this spot here later. Maybe I'll use green. And then the probability that x equals 5, we'll calculate that later. But I just want to show you where stuff is coming from. So the probability that x equals 4, remember, we have 5 trials, so we have 5, choose 4. The probability of success is 0.56 to the power of k, which is 4. And then 1 minus 0.56, let's just do it here, and then we can just use it, 0.44 to the power of 5 minus 4, right? 5 trials, 4 successes means 1 failure. So 0.44 to the power of 1. 5 choose 4. This is a great opportunity to make sure that you've got your choose function out of control. Under control. 5 choose 4 gets me to 5. 0.56 to the power of 4 is roughly 0.098344496. If you can, or whenever you can rather, keep all your decimal places. So not just the ones that show up on your screen. Use whatever your calculator has because it has more values stored. It just can't show them to you. And so keep this on the display. And then because these are easy enough to deal with, right, I'm going to multiply that by 0.44 and then multiply by 5. You want to keep as many, especially for binomial distributions, keep all your decimal places. Keep all decimal places. Right. Until the very end. And usually there will be instructions like round your answer to 4 decimal places or something like that. But keep all your decimal places until then. So take what's on your screen times 0.44 times 5, and I end up with 0.216358912. Okay. Oh, sorry, I gotta help her out here. Okay, so that's the probability of exactly 4 successes or 4 increases in the 5 weeks. So now we're gonna do the probability that x equals 5. And I guess I should have used a different color than pink. I tend to use pink as like a general highlight my text color. I just like it, it's cute. So now the probability that x equals 5 is 5 choose 5 times 0.56 to the power of 5 times 0.44 to the power of what? 0, right? Because there are 0 failures if we have 5 successes. Or if you prefer to use the formula, right? 5 minus 5 is 0. 5 choose 5, 5, 5, 5 is 1. There's only one way to have all 5 successes. So it's 1 times, and then 0.56 to the power, 0.56 to the power of 5 is 0.0550731776 times anything to the power of 0 is 1. So that is just the probability, right? Because 1 times 0.055 times 1 puts me at just 0.05507317776. So then if I kind of flash back to what we were trying to solve for, copy, I now have what I need to do that. So this becomes the probability that X is 4 is 0.216358912 plus the probability that X is 5 is 0.05507317776. So if I add those together, and I'm only going to do these because I didn't store it, but plus 0.216358912. So there's a chance I entered it incorrectly, but just go with it. 0.271432086. That's the probability of an increase in either 4 or the 5 weeks, or as I phrased it, more than 3 weeks, right? Not including 3 weeks. The more than 3 weeks, it can be a little bit tricky to know if you should include 3 or not. So that's why I often specify. Good, great. Okay. So this, oh, one more. We were almost done. I almost forgot. But finding the mean and the standard deviation are pretty breezy. But we'll need them for the next section. So remember, mu is n times p. Yeah? And so in our case, mu is going to be 5 times 0.56. So 5 times 0.56, mu is 2.8. 2.8 is not going to happen, but that's how many times, how many weeks out of 5 in 5-week increments we would expect to see an increase, 2.8, which is more than half. So that's good. Right, but that is because of the 0.56, right? And so here, this really means we expect 2.8 increases in 5 weeks, right? We're not going to see 2.8 because we're counting in 0, 1, 2, 3, 4, 5. But on average, we would expect 2.8 increases per week. Sigma is the square root of NPQ. Remember, Q is 1 minus P, right? Or sigma is the square root of NP times 1 minus P. But I like NPQ. It has a nice ring to it, so I'm going to use that. Sigma is the square root of 5 times 0.56 times 0.44. Remember, we already found Q, right? So you can just use it now. 5 times 0.56 times 0.44. Sigma is the square root of 1.232. I'm highlighting this step because often the problem that people have is they forget to take the square root, right? They do this multiplication and then forget the square root. So once you square root it, I'm getting a sigma of 1.109954954. And you can round that to whatever it tells you to round it to. Maybe 2 decimal places, 1.11. Nice. But it doesn't specify and we're not using it, so I'll just leave it. Nice. There's this fly in here and I've been trying to trap it to put it outside, but it just will not cooperate. He likes it here. Okay. So this is where things get really kind of cool, kind of weird, kind of, I don't know how to feel about it, right? And so Well, I think it's cool. It is cool. But what happens if our number of trials is large enough? Our binomial distribution, remember binomial success failure, our binomial distribution starts to morph into a normal distribution. What? With a mean mu and a standard deviation sigma that we just were able to calculate. So that's kind of weird, but also pretty cool, right? And so when the number of possible outcomes is large, right, or say the large number of trials, we can use a normal approximation to calculate binomial probabilities. So we use mu as n times p and sigma is the root of n pq. So as our mean and standard deviation for z-score calculation. So all of a sudden we're incorporating z-scores. So you can see this is why we had to hold off on introducing the binomial distribution. Otherwise it would have belonged very nicely in chapter 2, right? But we hadn't introduced the z-score and the normal distribution yet. And so this is the reason that we kind of had to hold it back. So what we're going to be able to do is we're going to be able to use z-score calculations for binomial outcomes, assuming we have in a large enough number of trials. Okay. And so we can use the normal approximation to the binomial as long as we expect at least 10 successes and 10 failures. Remember, there's that word expect again. And the expected value is the mean, right? Which we find by n times p. So now if I'm expecting at least 10 successes, what I'm saying, how we check it is we take n times p, that's the number of successes that I'm expecting. And we have to make sure that it's more than 10 successes. And then I also have to check that I have at least 10 failures, or I'm able to get at least 10 failures out of this n that I have. And so n times q also has to be larger than 10. This means that, okay, if I need a minimum of 10 successes and 10 failures, the absolute smallest number of trials that we can use this for is 20, right? And that's if we have an even 50-50 split, which is pretty rare. So we need a large number of trials in order to use this. But once we do, it's what you'll want to use, because you don't want to do these even using the binomial distribution like we did here, right, with more than 3 weeks, right? Now imagine you had 20 trials, right? So you're looking, instead of 5 weeks, you're looking at 20 weeks. What's the probability of at least 10 increases in those 20 weeks? Well, that's 10, 11, 12, 13, 14, all the way to 20, right? And so you would have to find that, and that just sounds like a lot of work, right? And so so we don't want to do that. So that's why we have the normal approximation. So that's pretty neat. Okay. So, right, we're going to lead up to using a z-score calculation, but I'm going to show you by way of example, right? Okay. Guess I better bring this in here. Oops. Oopsies. How can I adjust it? It won't let me fix it. Okay, sorry. Please stay on the line. There. It won't let me like scroll and grab something. Okay. And then I can delete this. Okay. Off to the races now. All right. So that's what we were talking about. Okay, so here's the, uh-oh, my pen's not connecting. Okay, it's like everything's falling apart right at the end. All right, so suppose that Canadian Blood Services anticipates the need for at least 1,850 units of O negative blood for a particular region this year. Seems perfectly reasonable, and you can imagine that they do these types of calculations, right? So it estimates that it will collect blood from 32,000 donors, and only about 6% of people have O negative blood. So just like before, right, I encourage you, I'm not going to read through these questions with you, but I encourage you to pause it here and work through these to see how much of it you have, and then fill in the gaps with me later, right? So you can pause it now. There. Okay, so welcome back. And we want to talk about what is a success in this case. So a success in this case is having O negative blood, right? Because we're interested in, okay, we're concerned with the number of units of O negative blood. We have the probability of O negative blood. And presumably, if you read through these questions, they're going to be about O negative blood. So a success is a donor with O negative blood. All right. What are N and P in this case? N is the number of trials, right? And so N is how many times are we attempting to get O negative blood? And so we are having to use an estimate, right? So we're guessing we'll get around 32,000 donors. We just put out an ad this weekend, blah, 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 right? And so they have a pretty good idea of the numbers that they're expecting. Of course, things go out the window if they only get 15,000 donors, but it's a good start, right? So in terms of the number of trials, we're going to have 32,000 donors. And so N is 32,000. Imagine making that tree diagram. No, thank you. Right. First person, O negative, not O negative. Second person, O negative, not O negative. O negative, not O negative. Right. Ugh, gross. And what's P in this case? P is the probability of success. And the probability that a person has O negative blood is 6%. So 0.06. What is the mean and standard deviation of the distribution? Mu is N times P, which in this case is 32,000 times 0.56. So how many, or sorry, 0.56, that's from before, 0.06. Big difference. How many are we expecting? How many O negatives are we expecting? 32,000 times 0.06. Hopefully you get the same thing. Mu is 1,920. Make sure I didn't make a typo here. And then to keep it on the same page, we've got sigma is the square root of N times P times Q. So sigma is the square root of 32,000 times 0.06 times 0.94, which I'll confirm 1 minus 0.06, but hey, nice. So 0.94 times 0.06 times 32,000. And then don't forget to square root that. I get a sigma of 42.48293775. And I'm going to round it to 42.48 to 2 decimal places. That's not set in stone. I'm just kind of going for it here. And of course, in a quiz or on a test or whatever, it would tell you how many decimal places to give me. Okay. So we have the mean and we have the standard deviation. Good. So now it wants us to set up the formula, and there's a reason it just wants us to set it up. And that's because we're not going to be able to we're not going to be able to use the choose function. Our calculators are just going to throw their hands in the air and say, no, I can't do that, right? So that's why we're just setting it up. But it's good to see what's going on. For getting exactly 1,850 units of O-negative blood from 32,000 donors. So that's the probability that X equals K. I'll just write out the general formula, right? Is N choose K times P to the K times 1 minus P to the N minus K. So the probability that X equals 1850 is 32,000 choose 1850 times 0.06 to the power of 1850 times 0.94 to the power of 32,000 minus 1850, which is 30,150. So we're dealing with kind of huge, weird numbers here. And so that's why we're just setting it up, right? You can try 32,000 choose 1850, but I get a math error, right? Too large for calculator to handle. Ooh, crazy. But that's okay. That's what you would do but that's for exactly 1850. Okay. So then if you wanted to know the probability of 1850 or more, well, then you'd have to do 1850 just like this, plus this, but with 1851, plus this with 1852, and so on and so forth, all the way up to 32,000. Right? No. We're not going to do that. That's why we have the normal approximation. Someone was thinking, hey, there's got to be an easier way. It's insane. And there is. It's an approximation, but it's a pretty good approximation. So we're going to check the assumptions for the normal approximation to the binomial. So in terms of the binomial, we have assumptions, right? We said, okay, our probabilities or our events have to be independent of each other, which they are. People's blood types are independent. You know, you get 32,000 people at a clinic, unless, you know, you're getting some sort of family extravaganza, you can assume that that's independent, that those O negatives are all independent, or all the blood types are independent of each other. And the other thing is we have to have only 2 possible outcomes. And we have established that we're saying O negative is a positive or is a success and not O negative is a failure. So in terms of our assumptions, what we have to check then for the normal approximation is we need to make sure we have at least 10 expected successes and failures each, right? But I'm assuming that that's clear. So N times P is, we already found it, was because we already did n times p was 1920. 1920, which is more than 10. And so I like to put a little like check mark. Yeah, it checks out. Good. We're good to go. And then n times q. There are two ways that you could find it. You could take 32,000 minus 1920. That's the number of failures. That's the expected number of failures. Or if you want, you can do 32,000 times 0.44. It should get you to the same spot anyways. So 32,000 times 0.94. And I'm going to multiply across here so I get them kind of underneath each other. 32,000 times 0.94 is 30,080. But also notice that this is that 32,000 minus 1920 is also 3080 or 30,080. So either way you could have got there, but if you like the formula, then that's fine. Which is definitely more than 10, so that checks out as well. So therefore, the assumptions for the normal approximation are satisfied. Yeah. So we haven't really seen what that means for us, but we're about to. Okay. So for this last problem, we are going to solve this here. How likely is Canadian Blood Services to meet its need of at least 1,850 units of O negative blood? Okay. So we know from here, we check the assumptions, so we're allowed to use the normal approximation. So what we can do is we can draw this distribution of O negative donors with a mean of 1920 and a sigma of, what did we say? 42.48. Let's use the rounded value, that's fine. 42.48. Okay. So here I'm expecting 1,920 O negative donors, but we want to find the probability of at least, right? So how likely, that's really asking what's the probability, but remember the probability is the area under the curve. So to meet its need of at least 1,850. So that's going to map to something like this. And the area that we're interested in is this area, right? Okay. So this is looking a lot like part 1 of chapter 3, right? Now I can just find a z-score, and sure enough, z equals x minus mu over sigma. And in this case, z is 1850 because that's the value that I'm interested in. So that's always going to be your x. Minus 1920 over 42.48. And I'm going to try to keep it on one page here. So I'm going to zip this up a little bit. And say Z is 1850 minus 1920 divided by 42.48. So I get a Z of negative 1.647834275. Z, remember, is always rounded to 2 decimal places because that's how many we have in the table. And so Z is negative 1.65 to 2 decimal places, right? And if you need to brush up on your rounding, it's because 4 was followed by a value larger than or equal to 5, and so that's why we rounded up. Okay, so now using the Z table, we find the area to the left. Remember, it only gives you the area to the left of Z equals negative 1.65 is, now let's go find it. So negative 1.65, again, I'm going to delete some of this here. Negative 1.65. 0.0495. 0.0495. So the area to the right is 1 minus 0.0495, which is 0.9505. Nice. Good. All right. What is that? That is the probability, or how likely they are to meet their need of at least 1850 units of O negative blood, right? Imagine even if you kind of cheated and, well, kind of got clever and jiggy with it, even if you found the probability of 0 O negative plus 1 plus 2 plus 3 all the way up to 1850 and then subtracted that from 1, right? That's probably the kind of easiest way you would do it if you had to do it by hand. That's still a lot of calculations, 1,851 to be exact. So no, I don't want to do that. So I'm okay to use this approximation because it's actually a really good approximation. So that's pretty cool, especially for large sample sizes like this. So the probability that they meet their need is 95.05%. Therefore, the probability they meet MEA, meet their need is 0.9505 or 95.05%. Whee! Nice. So kind of a fun way to tie together the binomial distribution and the normal distribution. But yeah, nice work. All right, see you next time.